Great, thanks, Alex. And yeah, so as I promised in my little 10-minute introductory blurb last week, I'll be talking about the Klein Gordon equation. Box G applied to an unknown function, which we'll call capital U in this talk. Little m is going to denote the mass of the field. I'll be discussing this on a class of spacetimes. I'll say a little bit more about the precise assumptions in a bit. So capital X will be the spatial slices, G will be the metric, and these are going to be static, hence the static in the title, and asymptotically Schwarzschild. And one quick asterisk on that, I'll be saying asymptotically Schwarzschild throughout the talk, but everything that I say applies equally well to asymptotically Reiessner-Nordstrom spacetimes. It's just that's somehow one extra word to say. And maybe charged black holes don't capture the imagination in the same way as ordinary black holes. So I'm going to say asymptotically Schwarzschild. Now X here is going to be some manifold with boundary. Well, actually, so in the paper on which this talk is based, X is pretty much completely general manifold with boundary. But to be maximally definite, let's just take X to be the ball, the 3 ball, that you get by taking R3 and then radially compactifying it. So in fact, I think it's probably safe just to forget the compactification if you really don't care. And I hope that everything that I'll say is going to make sense. And the metric G is going to look like the following. So it's going to be static, so nothing's going to depend on time, which is very good. And I'll say just regarding sign conventions, you can always assume throughout the talk that whatever, my sign convention is always what it takes, what is required to make what I write on the board not be wrong. I can't guarantee that that'll be the same sign convention throughout the talk, but hopefully I managed. Okay, so the metric is going to be a sum of 2 things. There's a Riemannian metric, G sub x, on x. That's, once again, time independent. And the time component is going to look like this. Capital M is supposed to be interpreted as being the mass of the astrophysical body that's generated in the gravitational field. You might complain that my conventions for factors of 2 differ from the usual one, but you can just say we're working in a system of units where the gravitational constant is equal to 1/2. Okay, whatever. I'm not going to be completely precise about what's being required of this sub-leading term here. Obviously, I want it to be decaying like 1 over r squared as r goes to infinity. But you also want some control of derivatives. Okay, it turns out that symbolic estimates suffice, but maybe don't worry about that too much. And I should say that really, if I was being careful, I would have Japanese brackets on all of the r's here, because I don't want any conical singularities anywhere. I'm going to be very sloppy about this throughout the talk. So r here is supposed to be the Euclidean radial coordinate on R3, but maybe it's best to just think of r as being the reciprocal of some boundary defining function of the boundary of x. So, if I was to write things in the notation of Richard Melrose, and I might get in trouble with this because Maciek just showed up, but if x is a boundary defining function for the boundary of x, then r is just 1 over x. So maybe it's really a Japanese bracket of r, but whatever. So g of x is going to be a Riemannian metric on x, like I said, of the following form. Whereas again, same assumptions as up here. And lower order means lower order in the sense of decay. So everything that's here should be decaying at some suitably high power of r as r goes to infinity. And this guy here is just the ordinary spherical area element on the sphere at infinity. I should say that even though I'm requiring spherical symmetry for all the leading order terms here, there are no symmetry assumptions at all to be placed on the lower order guys. So really no assumptions there. And yeah, this is an asymptotically Schwarzschild spacetime, because if you look at the leading order parts, which consist of that, and then these guys here, then that is the Schwarzschild metric. So these are asymptotically Schwarzschild. And if I was considering the Reiessner-Nordstrom case, then the relevant modifications would be in these lower order terms. Now it's a little bit misleading actually to say that this is sort of modeled on the Schwarzschild spacetime, because there's no event horizon, and that's actually very important. So I'm going to write that in big letters. That's kind of implicit in this formulation. I mean, this form of the metric is only to be required near the boundary of x. It's the only place where this really makes sense anyways, or says anything interesting. I'm using spherical coordinates. So there's no event horizon. So really, it's more accurate to say that these spacetimes are going to be modeled on the Schwarzschild exterior. But even that, I think, is slightly misleading, because the Schwarzschild exterior has two asymptotic ends. There's, of course, the end where r is going to infinity, so the large end of the spacetime. And there's also the horizon itself, which, if we're shifting attention to the exterior, is another asymptotic end. And the spacetimes, these x's here, only have one asymptotic end, namely that modeled on the large end of the Schwarzschild exterior. So I'm going to be a little bit sloppy, though, and just say that these things are modeled on the Schwarzschild exterior. So that is the problem. I should say that I think the tendency of a lot of mathematicians and physicists when seeing a setup like this is to say, okay, it's a little bit contrived. But I want to stress that these sorts of spacetimes are actually plentiful in nature. So, a very simple example to keep in mind is the case where the spatial slices x are just isometric to the Schwarzschild exterior outside of some compact subset K of the interior. Right, so that's certainly asymptotically Schwarzschild in really the strongest possible sense. And these sorts of metrics are ubiquitous in nature as describing the gravitational field configurations generated by astrophysical bodies that, one, have negligible rotation, and two, lack the sufficient density needed to form black holes. So, this includes things like the Earth and the Sun and stuff like that, as long as we can neglect rotation, which would make these, or if we were to take that into account, then the metrics would be stationary rather than static, and that changes the story quite dramatically. That is the setup. Maybe I'll say a word as to why the Klein Gordon equation. So if you're used to thinking about the motivation for the wave equation in general relativity as being setting the linearized Einstein equations, then maybe it's not so clear why you should care about the Klein Gordon equation. And of course, you give different motivations depending on whether you're a physicist or a mathematician or a mathematical physicist. So if you're a physicist, then one reason to care about this problem is if you care about modeling particles orbiting gravitational wells when two things hold. One, when you can neglect the back reaction of the particle on the spacetime itself. So this is certainly reasonable if you're looking at little particles orbiting black holes or stars or whatever. And the second assumption is that you can neglect the interactions between our isolated particle and everything else that it might come into contact with. So maybe this is not such a good model if you care about looking at particles inside the sun or inside the, I forget what it's called, the little charged cloud thing surrounding black holes. But okay. And actually, one particular scenario that physicists have actually considered in the actual literature is looking at dark matter particles orbiting various astrophysical bodies. So, dark matter is supposed to, by definition, not be interacting via the electromagnetic force, and so it's at least reasonable to expect that you can neglect interactions between that and everything but the gravitational field. If that's not accurate, then you could blame the physicists rather than me. If you're a mathematical physicist, then maybe you care sort of more fundamentally about the Einstein-Klein Gordon system. Okay, and it should at least be plausible that, or philosophically plausible that if you want to understand that, you should at least understand this sort of problem first. And maybe if you're a pure mathematician, then you just think that it's reasonably natural to add a zeroth order term to an equation, a PDE that you already care about. So there's several reasons to care about it. Now, why no horizon? Well, okay, if you bought what I said above, then maybe you don't need more convincing other than to say that it appears in nature. But there's another good reason to study it, which is even if you only care about what's going on black holes, then it should at least be plausible that it's worth simplifying the setup by getting rid of the horizon. I mean, getting rid of the horizon is getting rid of one asymptotic end, and that's one less thing to analyze. So at least it simplifies the problem. A more precise version of that would be to isolate features of the problem of studying Klein Gordon on the exact Schwarzschild spacetime that have to do with the structure of the large end. So that's actually, I want to elaborate a little bit more on that now. Okay, so specifically, here is a conjecture which can be extracted from the physics literature. And of course, I'm going to write a precise statement, and you can't find a precise statement to this effect in the physics literature. So insofar as what I write is wrong on technical grounds, then blame me and not the physicists. But okay, this can be extracted from a paper of Hod and Piran. I think this is in '98. And Koyama Tomimatsu in '01. And what this says is that if U is a solution to the Klein Gordon equation, the Klein Gordon on the exact Schwarzschild spacetime, with sufficiently nice initial data, and just to be concrete, let's say that I want the initial values of U, as well as the initial time derivatives of U, be Schwartz. So Schwartz at the large end in the usual sense and some comparable condition at the horizon. Then U decays pointwise. And more specifically, there's some, the various groups have made explicit conjectures about the rate. So Hod and Piran, on the basis of numerical work, said, okay, there's some decay. So the decay is at least little o1, but they said it's slower than any power law, and they didn't really have anything more precise than this. So this is from Hod and Piran. Then Koyama and Tomimatsu, using sort of quasi-mathematical argument, argued that the decay rate, and also they had numerics backing them up, should be this sort of funny-looking rate of t to the minus 5/6. Definitely a little bit intriguing. And although I must say, their argument, I don't find it entirely convincing. Right. As in, so this is for the exact Schwarzschild spacetime, where you have the horizon. Yeah. Oh, thanks for clarifying that. So yeah, so they predicted this t to the minus 5/6 rate. And I should say that there's not universal assent to this in the mathematical community. In fact, there's a rumor that's been spreading around for some time that in fact the best that one can say in general is a rate of 1/log t. And it's probably safer if I don't attribute this to anyone. So I'll just say this is due to the Grapevine. Okay. So this is still open. In fact, until this last year, there's basically been no mathematical progress towards establishing this. But this changed actually, I want to say 2 months ago, a couple months ago. I'll go over here. With the following very nice theorem of a trio. This is Pascalotto, Schlappentock-Rothman, and Van der Mortel, and I'll just write et al. And what they showed is that the predicted rate of t to the minus 5/6 holds if the initial data has only finitely many spherical harmonics in it. So I'll just write if the initial data has the form okay. Yeah, finitely many. And really what they do is they use separation of variables to reduce the case when it's a single one, and then once you have it for a single one, then okay, the case where there's finitely many follows immediately. And I think it's fair to say that their argument is basically a rigorized version of the original argument of Koyama Tomimatsu. I don't think there's too many new ideas in this paper that weren't present in this, but of course, it was a non-trivial amount of work for them to make this actually rigorous. But yeah, so I think there's nothing more that we should, there's not that much more that can be concluded from their original argument than the t to the minus 5/6 decay on individual spherical harmonics. Right, so that's what I was about to mention. I don't know the precise derivation. I asked several people, and I think, it's like a game of telephone. Somehow, the fact that it should be 1 over log t has passed the grapevine, but the actual argument has not. But, but the claim was something to the effect that even though the t to the minus 5/6 decay should hold for individual spherical harmonics, that it's somehow very hard to establish uniform control over the decay rate as the angular momentum number goes to infinity. And so when you try to control the sum over all angular momentum, this is somehow the best that you can get. Yeah, so certainly if you have some, you could be very weak, right? Because if you have nice, smooth initial data, then you have pretty good control. I haven't thought about this question in particular, but I think it's in general, I don't think it's easy to get uniform control as angular momentum goes to infinity. Exactly, so it's probably doable, but I haven't tried or thought about this very long, so I'm not really sure. Yeah, I really don't know. I mean, I personally think it would be quite surprising if this were true. I mean, somehow I find the fact that it works. Well, okay, fine. fine. Sharp. The true nature of things, how about that? Well, like I said, yeah, I mean, this is definitely what the rumor is. But yeah, I really can't say much more than that. I mean, like I said, I personally would put my money on this being correct, or this being correct. Yeah, don't hold me to that though. I mean, part of the reason why I want this to be true is that this then, somehow if this is the truth of the matter, or this is the best that one can say, then all possible all arguments that I could imagine that don't involve really hard estimates of ODEs would fail. So I want the simpler thing to be true. Okay. This is the latest progress. Oh, I should say this is just from this last year. Right. So let's assume though for a second that this conjecture is actually true. As in if, sorry, as in if, which M? On the, okay. Yeah, so on the case of Minkowski space, well then it's 3/2. Yeah, so it's significantly slower. That sounds like 3/2 to me, but I mean, so that case you can see it in exact Minkowski space. It's just simple stationary phase computation. Okay. Right, so that's Price's law. I'll get to, yeah. Well, I'll get to that. But anyway, assuming for the moment that the conjecture is true, a natural question to ask is, okay, if you start with some nice initial data and let it evolve over time, where does the L2 mass go? I mean, maybe it doesn't go, okay, I mean, yeah. I mean, that's what I'll eventually be proving, but the point is this is somehow, I mean, it's a very natural expectation, but somehow this is in tension with the conjecture. Anyway, so assuming that the conjecture is true, where does the L2 mass go? And there are sort of two reasonable possibilities. One is that it kind of diffuses outside of the gravitational well, and more of the L2 mass escapes to infinity. Maybe that's pretty counterintuitive, but as we'll see in a minute, this is kind of what happens for the massless wave equation. The second possibility is, well, maybe it sort of falls into the black hole slowly, or towards the horizon. And okay, of course, it must be admitted this is not a logical dichotomy, so maybe you can imagine more exotic scenarios where maybe the mass starts to fall in and then maybe bounces out and then falls in again, and then over time, it just spreads out more and more to get the requisite amount of decay. But I don't think that's particularly plausible, so something like one of these two possibilities should hold. And I mean, there's something very appealing about two, it sort of appeals to our childlike picture of how black holes work. But I initially thought it was likely one that was the case. And that's what I want to justify by sort of analogy with what happens for the massless wave equation. So there, the relevant statement is, as Maciek pointed out, it's called Price's law. So this is a piece of, I think, 1970s physics lore that there's been a huge amount of mathematical work on over the last, I think, 20 years or so, maybe a little bit less than that. And I'm not going to give a precise statement, but the following rough version should do for our purposes. So, on asymptotically Kerr, so this does not need to be static, but it includes the static case as a special case. So on asymptotically Kerr spacetimes, actually I should probably say spectrally reasonable. So on asymptotically Kerr spacetimes, then solutions to the massless wave equation ox gu u equals 0, with, of course, nice initial data, decay to t to the -3 rate. Okay, so, much faster rate than this, and faster than even Klein Gordon in the asymptotically flat case. And this spectrally reasonable parenthetical here is doing a bit of work. There's some kind of mode stability condition that's involved in this, and one also wants some kind of non-trapping condition to ensure that one gets control over things in the large energy regime. But these are relatively weak. So the important point is just that this applies on a very large class of asymptotically spacetimes. And in this amount of generality, I think it's fair to say that the definitive treatment is due to our esteemed organizer, Peter Hintz. So in his paper that has Price's law in the title, there's a precise statement, a precise version of this that really applies in quite a lot of generality. And one aspect of Hintz's argument that I sort of took to heart is that a horizon should not be necessary for the truth of things like this. I mean, the key aspect of Hintz's proof, or maybe it's more accurate to say the key aspect of the paper of András Vasi, on which this paper is based, is to analyze what's going on at the large end of the spatial slices. So, yeah. No, I mean, like I said, there's yeah. I mean, like I said, there is a precise. But am I correct? No, I don't think this is correct. No. So I think there's not. I haven't checked carefully a statement to this effect, but I think these spectrally reasonable conditions are sufficiently weak that you do get a very large class, that some of these spacetimes that we're considering here meet this criterion. And so solutions to the massless wave equation do decay on them. And like I said, somehow really the key thing that's going on in this analysis is understanding what's going on at large radii. I mean, of course, the fact in this spectrally reasonable condition, there are global conditions here. So one does really need a global analysis, but somehow the key thing seems to be what's going on at the large radii. So that was my reason for sort of expecting possibility 1 to hold, and I think I could say that Peter was also expecting possibility 1 to hold. Anyway, so yeah, so the original motivation for looking at this problem was to hopefully try to prove something like this conjecture, but in a simplified setting without the event horizon. And like I said, given that I thought that possibility 1 would hold, I thought that one could really do this. So the following theorem, therefore, came as a surprise. Oh, sure. I mean, of course. Okay. So one of the assumptions here is that you want the leading mass to be non-zero. Yeah. So I mean, yes, it's true that you can get faster decay if you kill off some of if you kill off terms in the metric at large distances. Yeah, I mean, there's also a more precise statement in this paper about sometimes you get better decay depending on which sphere core modes are absent, and I think in one of his more recent papers, there's also a discussion of some examples in which you get either better or worse decay. Yeah. Sort of an interesting thing. Okay. So the following theorem caught me by surprise. There's going to exist a sequence of positive real numbers converging down to 0, and some Schwartz functions, u sub n, and these are not identically 0, such that if we define u to be given by e to the plus or minus, the sign here is relevant, okay, define it to be this, then this solves the equation. So there exist standing wave solutions to the equation, and in particular, even if the initial data is Schwartz, then solutions to the Klein Gordon equation on these spacetimes do not need to decay. That's the claim. And this is the first sort of theorem of the talk, and based on the time I may get to present a second one that gives a quantitative version of this later, but I think it, at least in my mind, kind of conclusively kills off the possibility one. And the proof is actually embarrassingly easy, given how long I thought that possibility one was the thing that holds. So I'll sketch the proof, and I actually have time to go through the whole thing, or, whole thing modulo some details. Yes. It's not they're embedded. No, they're not embedded. No. You sort of see where this is going, of course. So the first observation is that there exists a Schrodinger operator P. This is a differential operator, second-order differential operator, on X, whose bound states yield standing waves solution that's above. Yeah, we'll see. Yeah, I mean, it's these are going to be eigenstates. I mean, this is eventually what's going to happen. Of course, is that the UN are going to be eigenstates of P. So the second observation is that P, okay, it's a Schrodinger operator, so we can look at the potential in it, V, and the potential has the form of this long-range attractive Coulomb or Newtonian potential. Maybe that should be extremely unsurprising, and then some short-range remainder. And now you can see what happens if either the black hole mass m, or the body mass m, or the field mass m are 0. Then this long-range term vanishes, and things are simpler. And of course, short-range Schrodinger operators can have a very different spectral theory from long-range operators. And one particular fact about Schrodinger operators on Rn of this form is that such operators have infinitely many bound states. And this is a slightly different setting than the familiar one from scattering theory, but everything works almost exactly the same. So this is really a very general spectral theoretic fact. So that's the sketch of the argument. And I hope you'll agree with me that it's very venue appropriate, I think. Like somehow the theorem is saying, like Alex already pointed out, that massive particles can get thrown into orbit around astrophysical bodies. And kind of amusingly, the proof is by comparison with the hydrogen atom. I mean, the canonical example of such a Schrodinger operator to keep in mind is the hydrogen atom. Okay, in that case, you do have an actual conical singularity, but it's sort of irrelevant for what we're talking about. And of course, that's what Schrodinger won the Nobel Prize for his work on the hydrogen atom. So I think it's venue appropriate. So I'll start with point one, which is, all these points are actually very easy once you sort of know what to look for. So first, consider the operator P naught of sigma, defined by right? Okay. And suppose that little u is an element of the kernel of this guy for one value, let's say call it sigma naught. Then we'll let u hat Let this be, let's see. Then capital U be the inverse Fourier transform U hat, and then U is just a function of the points in the manifold, so it just passes through this temporal Fourier transform, and then we get e to the, okay, there might be a constant depending on your conventions with the Fourier transform, and the sign here depends on your conventions with the Fourier transform, but okay. You get a standing wave. And if you apply the Klein Gordon operator, to U, then once you move all the Fourier transforms around, this is 0. So we've reduced the problem of producing standing waves to the problem of constructing elements of this kernel. Oh, I mean, of course, we want this to be non-zero, but okay. Now, P naught of sigma is not a Schrodinger operator just yet, so if you write out what it is, I mean, it's just an exercise to compute it. The result looks like the following. It looks like this, where this is some vector field on X, and then this is, of course, the Laplacian of our Riemannian sort of spatial slices. And this is not a Schrodinger operator because we have this annoying factor here on the sigma squared term, but okay, we can just multiply that by that through and it doesn't change the kernel. So this denominator here is coming from the metric, and so just by assumption, it has to be non-vanishing. And this is now the element. This is now an element of the spectral family of some Schrodinger operator. I mean, you should be a little careful because you have this factor here, but okay, call this a Schrodinger operator. So now define P by setting this whole thing equal to P plus M squared. I think it's plus. Right. Maybe. And so now the problem of constructing elements of the kernel of this is the same thing as constructing elements. So kernel of P naught of sigma is just the eigenspace, the eth eigenspace of this operator P. Okay. That's what P is, and that completes discussion of point 1. Now, if point 1 was just an exercise in evaluating some Fourier transforms, then point 2 is just an exercise in staring at the board. Because what is V? So V is just the result of when this whole factor here gets applied to M. and I have to subtract this m squared here. Okay, so as I claimed, result is the desired Newtonian term, and then some short range remainder. That completes discussion of point 2. Yeah, so of course there's an obvious annoyance here, which is that we had this first order term here, which is variable coefficient, and we multiplied this by this factor here. So it's not the case. So P is not self-adjoint, not even symmetric. On the usual, on just L2, that's associated metric. But this is actually quite easy to fix. The relevant fact here is that P with the usual domain, and it's not self-adjoint with respect to the original inner product, but it's self-adjoint with respect to a slightly modified inner product. Just rescale the density by the square root of this factor here. Yeah. And this is, if you want to just verify this, it's really just an exercise. Maybe, I'm not sure what computation you're referring to, but it's a very easy computation. So it sounds basically the same, but just with separation of variables. Yeah, I mean, it's a very elementary computation. If you want to see what's going on in more detail on, say, the exact Schwarzschild spacetime, then the standard thing to do is to absorb the factors here into the tortoise coordinate, just do a coordinate change and work with the tortoise coordinate. And then very concretely, what this volume element is here is just take the spherical volume element, but replace dr with dr tortoise. That's sort of very concretely what's going on. And yeah, this is very nice. So now we can sort of appeal to our, we can actually think about this spectral theoretically. Well, because L came from the metric. So it's sort of, yeah. All right, so then the theorem, which I'm going to write as a picture, is that the spectrum of P looks like the following. So if we draw it in the complex plane, and also this theorem, I should say, will surprise absolutely no one in the audience, but I'll write it anyways. We have some essential spectrum, which consists of the positive or the non-negative real axis. And then the discrete spectrum consists of infinitely many eigenvalues accumulating at 0 and nowhere else. So I think this is always a little bit tricky, but I think I took out the m. That's why I did that. Okay, so that's the claim, and given the structure P, this should surprise absolutely no one. Because the location of the essential spectrum is not, or the fact that it contains the non-negative real axis is not really important for what we're talking about, I just want to go over the, like I said, very standard reason why the discrete spectrum is infinite. That's the key point. So the first thing which I'll explain is why the spectrum of P, I guess, yeah, so why the portion of p in the negative real axis, why this is infinite. The proof is by the variational principle, or Rayleigh-Ritz, or whatever you want to call it. By the variational principle, it suffices to construct a sequence called V1, V2, dot, dot, dot. Okay, this should be in H2 or something. With disjoint support, pairwise disjoint support. And each having negative expectation value, or with p having negative expectation value in that state. And of course, this inner product is the one for this guy up here. Okay, so I got to construct these v's. And the kind of fun fact is a very stupid choice of v actually works, namely bump functions. We could take v sub n, let it be given by I times REN, where En is some number that we'll determine, and then chi, okay, this is some bump function, supported 1 or something like that. Doesn't really, the precise details don't matter, but supported not at 0. Okay, and so if En, we make En small enough, or the smaller En gets, then this is supported at larger and larger radii. And so if I've constructed finitely many of these guys, then if I take E sub n to be sufficiently small, then the next one of these will have disjoint support from everything constructed previously. Okay, so then why is it of negative expectation value? Well, if you evaluate, where is it? Oh, yeah. So I think En is not the energy, so right, where is it? Oh, yes, so sorry. Yes, thanks. Why is this negative? So if you compute it out, then, well, okay, we get one term from the derivatives in P falling on B. I'll just write this as derivatives. And then we get another term from the potential. Now I'm regretting my decision to use V for these test functions, but whatever. And so if you look at this term, then this ends up just being big O of 1 over r squared, where r is the lower bound of the radii at which these things are supported. I mean, the reason why this holds, it just reflects the behavior of derivatives under dilations, or in Melrosian terms, the fact that the Laplacian has B order -2. Yeah. Sorry, I mean, this is on an exact Schwarzschild. No, I don't. Oh, yeah. Yeah. Yeah, that is true. Yeah, these are like s orbitals, if you will. Yeah. And then if you look at this term, so the short range part of V just also is contributes to this O of 1 over r squared term. And then so we're left with expectation value of 1 over r in that state. And this is, I ran out of space, but this last term here is big omega of 1 over r. So if you take En to be sufficiently small, then these are supported at large enough radii such that this second term here dominates and the result is negative. No, I think you can just fine. I'll just add to the short range part. Yeah. What is in 1 over r squared? Yeah, so that's also short range. Yeah. Okay. So that completes the proof of this proposition. Let's see, do I have any more? I guess I have to erase something now. Oh man, I was hoping to go the whole talk without having to embarrass myself erasing. Close. Let's see, where is the... Yeah, I see it. Okay. That's true. That's true. I'm never going to learn if I don't conquer my fears. And not quite. Okay. All right, do I squeegee or just let it? Hey, don't laugh. The American system is vastly superior. Eraser should be dry. Okay. So the very last part of the proof is to show that the portion of the spectrum of P that's below 0, this is discrete. Which once again shouldn't surprise anyone, but okay, it's part of the proof. And I'm actually going to be very pithy about the argument here. The key point is that if E is not a non-negative real number, then P minus E is elliptic in the right sense. So of course, this is 0th order differentially, so regardless of the sign of E, this is always elliptic in sort of the ordinary sense in compact regions. But because one is working on a non-compact region, one needs to mean ellipticity in the sense that takes into account what's going on at large radii, and that can care about the sign here. And the important point is just that when P minus E, when E has the right sign, then this is elliptic in the right sense. And therefore, Fredholm, your favorite Fredholm estimates apply. So with the usual domain, and this is now Fredholm. Depends analytically on E. And analytic families of Fredholm operators have very nice properties, one of which is going to imply that the spectrum here has to be purely discrete. So that's all I'm going to write for that. And despite how simple it is, there's one thing about this that I think is sort of neat, which is we might be wondering what part of the argument fails if you try to apply it on the exact Schwarzschild spacetime, right? Because clearly something has to go wrong. And the answer is it's only this, everything else that we discussed so far works. It's just this very last step that fails. And the reason has to do with the fact that the horizon is an additional non-compact direction. And so if you want to get something like a Fredholm estimate, you need a notion of ellipticity in that direction as well. And there's a natural guess, actually. So if you write the operator there, so on the exact Schwarzschild spacetime, P looks very roughly like, I'm going to throw out a whole bunch of terms. So it looks like this near the horizon. This is the tortoise coordinate. And so this looks like the Laplacian in 1D. The problem is that this is on near the Schwarzschild in the black hole horizon. Black hole horizon, so on exact Schwarzschild near the horizon. And the key point is that the terms that had little m in it, these all end up being suppressed by exponentially decaying factors. And so the result is that instead of having the plus m squared that we had, only the minus sigma squared is left. And the point is this now has the wrong sign. So this is positive semi-definite, and this is negative semi-definite. So one has a failure of ellipticity in the relevant sense right at the horizon. And so if one were to look at the spectrum, inside, this is outside still. Yeah. If you write it in terms of the tortoise coordinate, this is just what it looks like. Anyway, the point is there's just a coordinate system in which this is what it looks like, very explicitly. Yeah, I mean, of course, if you want to extend the spacetime through the horizon, then you should not be working with this coordinate system. Because this coordinate system puts the horizon at r star equals minus infinity. And so I think if you look at the spectrum of P, is that the term? I think that's the term. Yeah. Yeah. Okay. Yeah. So I think if you were to look at the spectrum of P in the setting, then what you would see is that this formally discrete spectrum now is all part of the essential spectrum. And instead of being able to conclude the existence of eigenvalues from this argument, the only thing you can conclude is the fact that the essential spectrum sort of starts pretty low. And I think, yeah, I'll end the talk there.